Okay, in parts 2, 3, and 4 of the Lab Workshop 1B, we're going to apply statistical models to some business problems. So let's open a new sheet in this workbook. There, we've got a new sheet. And our first problem says that you have a house painting business and you're going to run a telemarketing campaign next week. 200 homeowners will be contacted. You estimate that 10% of these homeowners will sign a house painting contract with your company. We're to assume that homemakers make their decisions independently. What kind of probability distribution would fit this situation? Well, we're going to make a certain number of phone calls. We're going to make 200 phone calls, and the outcome of each phone call is either going to be a contract, we get a contract, or we don't get a contract. So we can call that a success or a failure. So that should remind us, that should sort of cue us to the fact that this is can probably be modeled by with the binomial distribution. So we're going to use the binomial distribution here. So our first question says, what is the probability that exactly 10 contracts will result from this campaign? So for the binomial distribution, we need to know the probability of success, and I'm going to put that in a cell so that we can just select it. And the probability of success, we said that 10% of homeowners will sign. We're estimating that 10% of homeowners will sign a contract with us. So our probability of success is 0.1. The number of calls that we're going to make is 200. So the probability that exactly 20 contracts result from the campaign is. So here's where I can use my statistical function in Excel. So I say equals, I'm using the binomial distribution, so I can choose that from the list here. The first thing it wants to know is the number of successes I'm interested in. So with any of these statistical functions, usually quite often they'll just say X. What they're looking for is the value of the random variable that you're interested in. So right now it's 20. I then put a comma. The number of trials, I can point to where we have 200 here. I want that to be an absolute reference, so I'll hit my function for key, comma. And now the probability of success. So I'll point to my probability of success. That, again, should be an absolute reference. And then a comma. And then it asks me, do I want it cumulative? So this question has asked the probability of exactly 20 contracts. So I do not want a cumulative probability here, so I will say false. I say enter, and it tells me that the probability that exactly 20 contracts will result from this campaign is 0.093636. So about 9.4% probability that we'll get exactly 20 contracts. The next question says, what is the probability that less than 15 contracts will result from this campaign? The probability that less than 15 contracts will result from the campaign is. So the probability that less than 15 contracts will result. Do I want to include the probability that 15 contracts will result? No, I don't. Do I include the probability that 14 contracts will result? Yes, because 14 is less than 15. 13 is less than 15. 12 is less than 15. So I can say equals binomial distribution. So the number I'm interested in is not 15, it's 14, because I'm talking about less than 15 contracts, not less than or equal to 15. So the value of the random variable I'm interested in is 14, comma, again, point to the number of trials, or yes, the number of calls, comma, the probability of success, comma, and this time I am interested in a cumulative probability, so I say true, because I want the probability of getting 13 plus the probability of getting 12 plus the probability of getting 11 plus the probability of getting 10, all the way down to the probability of getting 0 contracts. So the probability that less than 15 contracts will result from the campaign is again around 9%, 0.092946. The probability that more than 25 contracts will result from the campaign is the next question. So the probability that more than 25 contracts will result from the campaign. And you can see where this might be of interest to you as a house painting contractor. If you get more than 25 contracts, you may have to hire an additional crew. So you wanted to know what's the probability that I will have to hire that additional crew. So more than 25 contracts. Do I include 25? No, I don't. More than 25 is 26 and up. But because it's 26 and up, I'm actually going to have to take 1 minus 25 and down. It's easier to draw a little diagram to show yourself this. So this is equal to 1 minus the binomial distribution probability of 25 is the value of the random variable we're interested in, comma, 200, comma, 0.1, comma, and again, I want a cumulative distribution. So it looks like there's about a 10% chance that I will get more than 25 contracts from this campaign, and I would have to hire my additional crew. So that's an example of the binomial distribution. Let's name this sheet binomial. Oh, no, we're going to name it telemarketing campaign. Let's insert a new worksheet, again, for part 3. Part 3 says that a haircutting salon has an average of 20 customers arriving each day. To cover its overhead expenses, the salon needs at least 16 customers per day. So we're creating a new sheet. We're going to name it Hair Salon. So I'll just rename it down here. And use it to answer the following question. So what is the probability that the salon will not be able to cover its expenses on any single day? So the first thing we have to do is figure out what kind of probability distribution we should be using here. We're looking at the arrival of customers in a day. And that you should recognize as a situation that could possibly be modeled by the Poisson distribution. It's a discrete distribution. Our random variable is the number of customers. It has to be a whole number. And Poisson distribution models the number of events that occur over an interval, usually of time. So the arrival of a customer would be an event, and we're looking at it over a day. So we'll try this using the Poisson distribution. For the Poisson distribution, the parameter that we need to know is what's the average number of events that happen over a particular interval. And we've been told that the salon has an average of 20 customers arriving per day. So that's lambda, our parameter is 20. And then we want to know what's the probability that the salon will not be able to cover its expenses on any single day. We're told that the salon needs at least 16 customers in order to cover its expenses. So if it gets 16 customers, it does cover its expenses. If it gets 16 or more, it covers its expenses. If it gets 15 customers, it doesn't cover its expenses. So we want to know what's the probability that there will be 15 or less customers in a day. So the probability of 15 or less customers in a day is, so this is equal to Poisson distribution. The value of the random variable we're interested in here is 15, comma. The mean, the lambda value, is 20, comma, and I want a cumulative distribution because I want the probability for up to and including 15. So it tells me that probability is 0.1565. The last part of the question says plot the probability distribution for between 10 and 30 customers. So let's do that. We'll set up a probability distribution table here. So for that we need values of x and then the probability of each of those values of x. So we're told to do it for 10 to 20. So 10, 11, 12. Another trick with Excel, if you're doing a series of any kind, once you put in a few values for that series, if you put your cursor on the bottom right-hand corner of the box and drag down, it will go down and complete the series as far as you want. So I can get my values of x from 10 to 30. So now I want the probability of each of those. So this is equal to Poisson distribution. The value of the random variable I will find over in column A, comma, mean is up here, my lambda value. I need that to be an absolute reference, comma, and to plot the probability distribution, I do not want cumulative, so I'm going to say false here. Enter. So that's the probability of getting 10 customers in a day. I should be able to copy this down for the rest of the values. So we see the highest probabilities are around 20, where our average is. So we want to plot this. We want to plot these values. So I will highlight them, insert column chart, and we see it like this. Now I have to do a few things with this column chart. I'm going to put a title on it. So this is Poisson distribution for hair salon. The y-axis is now probabilities. The x-axis is number of customers per day. And I have to change the values of the axis here because that should be 10 to 30. So I can go and select data, edit, show it where I want to get the data for that axis, say OK, and now it's showing up properly. I can get rid of this legend. Oh, I can correct my spelling. I can also, if I'm doing this, I may have been doing this analysis. I have a friend who's interested in buying the salon, so I want to highlight when the salon would not cover its expenses. So we're saying that that is 15 or less. So if I right click, again, just another way of customizing charts, if I right click on the bar, I highlight all of the bars, I select all of the bars. If I right click again, I should be able to just select one bar. There it is. I just get one bar. And at that point, I can format data series, go to my fill, say solid fill, but I want red to show that that's different. Format data point, fill, red. Should highlight, there we go. Okay, I close. I can then do that for all of these data points. And I can do that again with my F4 button, the function 4 button. Will just repeat what you've done as you click on each of the other bars in that series. Okay. So I've highlighted the number of customers where I do not cover my overhead expenses on any particular day. So that's the Poisson distribution. Part 4 of the assignment deals with the normal distribution. So we're going to create a new sheet. We're going to name it Spubbly. So part 4 says the Spubbly soft drink is sold in 2-liter bottles. Because of the variation in the filling process, bottles have a mean of 2,000 milliliters and a standard deviation of 20 milliliters normally distributed. So we know that this is the normal distribution. We have a mean of 2,000 milliliters, or 2-liter bottles, and a standard deviation of 20 milliliters. Our questions ask, first question says, if the process overfills the bottle by more than 60 milliliters, the overflow will cause a malfunction in the machinery. What's the probability of this occurring? Okay. So we're interested in the probability of overfilling the bottle by more than 60 milliliters. So if we overfill the bottle by more than 60 milliliters, what is the value of the random variable is the amount of liquid in the bottle. What is the value of the random variable we're interested in? And if the mean is 2,000, then overfilling, we're talking about filling more than the average, would be overfilling by 60 milliliters would mean that if we fill to 2,060 milliliters or more, that's when we'll cause a malfunction in the machine. So the probability, we want to know the probability that the fill will be more than 2,060 milliliters. So that's what we want to calculate. So again, with the normal distribution is a continuous distribution. We know that the area under the curve has to be equal to 1. We're talking about more than a certain value. So the Excel is going to give us a probability of up to and including a certain variable. So we are going to have to take 1 minus the probability that the fill will be less than 2,060 milliliters. So we're going to say equals 1 minus, and then use the function normal distribution. My value of x is 2060, and then comma. My mean is 2,000, comma. Standard deviation is 20, comma. And with the continuous distribution, you always want a cumulative. So we always say true here with any continuous distribution. So the probability that we will cause a malfunction with our machinery, with this filling mechanism, is quite small, right? It's 0.1%. Second question says, what's the probability of underfilling the bottles by 30 milliliters or more? So, probability that the fill will be less than, so underfilling is, we're interested in 30 milliliters less than 2,000, so that's 1970 milliliters. And that's going to be equal to, so equals normal distribution. Value of x is 1970, comma, my mean is 2,000, comma, standard deviation is 20, comma, and true. So there's a approximately a 6.7% chance that the fill will be less than 1970. And then the last question is 25% of bottles have less than how many milliliters? So 25% of bottles have less than how many milliliters? So we'll get a value in this cell. And we'll put milliliters here. So this is an example of when we need to use the inverse function. The inverse function will give us a value of the random variable that coincides with a certain probability. So we want to say equals normal inverse. Use the inverse function. The probability we're interested in is 0.25, always express probability as a decimal, comma, the mean is 2,000, comma, standard deviation is 20, and say enter. So 25% of the bottles will have less than 1,986.51 milliliters. So that's the end of Parts 2, 3, and 4 for Workshop 1B.